Okay. Yeah. Hi, everyone. I am Nilotpal from Weizmann Institute of Science, PhD student, of course. And I'll be talking about how we are doing jet flavor tagging with graph neural networks. So the theme of the talk will be slightly different, but jet flavor tagging is still very much tied to tracks, and we will see as we progress. So this is the plan for the next 15 minutes. So I'll start with talking a bit about the current Atlas jet flavor tagging setup. So jet flavor tagging is essentially identifying jets as a B, C, or light flavored. And to identify that, so we mainly depend on the tracks, and we mainly look at two key signatures. So in case of like B jets or sometimes for C jets, you usually have a displaced secondary vertex. So we try to identify and use information, try to use information about these secondary vertices. Also, you have some large impact parameters in such cases. So these are the two key signatures that we try to exploit when we're doing jet flavor tagging. Okay, so that's where we will start. And then we will talk about why we may want a new tagger. And that will lead us to the new tagger. And then we have some performance plot and some summary slide. Okay, so this is how we do jet flavor tagging in Atlas currently. So you start with a jet, and then the jet will have a bunch of associated tracks with it. And so we'll have the variables for the jet and also variables for the tracks. And we take these inputs and pass it to some low-level taggers. So these taggers are specifically designed to exploit these two key signatures that I just talked about. So you have some low-level taggers that are based on impact parameters, and some of the taggers are based on like secondary vertexing. And the goal of these low-level taggers is to extract some physics-based information. Then that we can take those information and pass it to a high-level tagger, so which is essentially some like multi-layer perceptron. In this case, like a DL1R, and this high-level tagger will give us the probability of the jet being a B, C, or light flavored jet. So once you have these probabilities, then you can use those probabilities to construct like a discriminant for, let's say, B jets. And once you get the discriminant, you can put a threshold somewhere, and you can say if it's above the threshold, then we will call it a B jet. And if it's below, then we'll say that it's not a B jet. Okay, so in this setup, the low-level taggers are very much important because it gives us this physics information that I just talked about. And it turned out that if you remove these low-level taggers, then the setup usually doesn't work. You have a significant loss in terms of performance. Although all-in-one tagger where we don't have these low-level taggers, it will be very ideal for us because you can remove these low-level taggers, so you'll have less moving parts. So it will be very easy to train and very easy to maintain. And also, if you have such an all-in-one tagger, then you can also easily optimize it for a variety of other use cases. The optimization will be very trivial in this case. But in practice, it's a bit tricky. Again, as I said, we need those physics information that we have from the low-level taggers. So to have a tool that does this classification, but also can extract those physics information, it's a bit tricky. And as a solution, it leads us to GN1. So GN1 is a new graph neural network-based flavor tagging algorithm. And the idea here is that instead of feeding those physics information as input to the high-level taggers, we define them as learning objectives. So the network will have its primary objective, which is to learn its the probability of it being like a BC or light jet. But additionally, we will define some training objectives that will guide the network to run a relevant representation of the jets, which will also encode this physics information in its hidden space. So this is like a schematic for this idea. So you have your inputs goes to the network, and on the bottom you have your primary task, which is predicting whether it's a P, like the probabilities for the jet being a P, B, C, or light jet. But additionally, you have these two auxiliary tasks. So the first one is the task of vertexing. So for each track pair, you try to predict whether they came from the same vertex, same origin. And the second task is for each track, you try to predict whether it came from its track origin, essentially. So whether it came from a B, a C, or a tau, or a primary vertex, let's say. So we call these tasks as auxiliary tasks, and the idea is that learning these auxiliary tasks will also guide the network in doing a better job with respect to the primary task. So now we can look at the inputs that we are using for this classification task. So essentially we have two JAD input and some track inputs. So I won't go through all of them. These are kind of the standard inputs, mostly the standard input that we use for flavor tagging in Atlas at least. I will just mention the last one for track inputs, which is lepton ID. So if the track is used in reconstruction of an electron, muon, or like in that case, we take the ID of those lepton, and that's some like an optional input. So later, when we look at the plots, we will see two versions of the tagger, one with this and one without. So that's why I thought I'll just mention it here. So we'll have two models, one with GN1 and one with GN1 lab. Okay, so once we have these two types of inputs, so how do we use it? That's shown in the figure. So you have your JAD input, which is just two numbers for each JAD, and you have a track input, so a feature vector for each track. And then what we do, we take the JAD input, the JAD feature vector, and concatenate it to each of the track inputs. And this kind of gives us the combined input for each track, and that will be the input for our network. So here we can see like a overview of the complete architecture that's being used. So we start with the combined inputs that I just defined, and they go through a track initializer, which is essentially transform it to a hidden representation. And then it goes through a GNN, which is a graph attention transformer in this case. But the idea is that the tracks kind of get to talk to each other, so there will be exchange of information. And from that, you can construct a track representation, which is also conditioned on its neighborhood. And once you're at that stage, then it kind of splits into three tasks. So first one is you take all this track representation and you pull them into one single representation for each graph. And then that goes through a network, and it kind of gives us the probability of the JAD being like a BC or light flavored. Then the second task is that you take all the track representation, you concatenate with the global representation that's shown in the top, the full representation. And then it goes through some another network, and then it does the first auxiliary task, which is to predict the origin of the track. And then also we have the third auxiliary task, where we take all the tracks and we pair them. And for each pair, we try to predict if they came from the same vertex or not. So this is essentially the network architecture. So now we can look at some performance plot. So as I said, the network will tell us the probabilities whether the light is whether the jet is a BZ, CZ, or light jet. And from those probabilities, we can construct like a 1D discriminant defined this way. And the plot shows the distribution of the discriminant for different flavors for both DL1R, which is like the current Atlas flavor tagging algorithm, and also for GN1. So right from the plot, you can see that the distribution with GN1 for BZ is shifted towards right compared to DL1R. And also it's shifted towards left for light and charm jet. So from this plot, you kind of get a qualitative idea of that with the new architecture, we are doing a better separation. And also, like once you have this plot, you can put a threshold somewhere, and that kind of defines your working point. So if your jet is above the threshold, you would call it a B jet. Okay, so this kind of gives us a qualitative idea, but if you want to get like a quantitative idea of the improvement, we can look at some log curves. So here we are looking at the B jet efficiency versus light jet and C jet rejection. So in this plot, each point corresponds to one threshold in the previous plot that I showed. So you choose a threshold, and based on the threshold, you will get some B tagging efficiency and some C and light jet rejection. And then you can move your threshold around, and for each value, you will get a new efficiency and rejection. And that's how you can make these plots. So on the top, we have the plots for TT bar. So look at TT bar because it's like a good representative of standard model process, and it covers the low PT region. And you can clearly see a very good improvement with GN1 compared to DL1R, which is like the current standard. And if you want to quote some numbers, so at 70% the efficiency, which is like one of the common working point that's used in the analysis. So you see like a 2.4 times improvement in terms of charm rejection with GN1, and also the light rejection improves by 1.7 times. So similarly, we can also look at the plots for Z prime, which is like a representative of BSM processor, and it kind of covers the high pitch region. So the 70% B efficiency working point in TT bar, it corresponds to a 30% B efficiency working point in Z prime. So there also we see a good improvement, and like at 30% B efficiency, we see like 3 times more C rejection and like 6 times more light jet rejection for the same given B efficiency. And also like including this lepton ID that I mentioned in the input slide, it shows that it also helps in improving the performance further. We can also look at the C-tagging performance. So how we do it, again, you have like, you get the probability score out of the network, and using those probability score, we can also construct a discriminant for charm tagging. And again, that leads to these plots the same way we had before. And again, we see a very good improvement with respect to the EL1R from GN1. I think here are some numbers. So at like 25% C efficiency, we see almost twice the amount of B and light rejection with new version. And for Z prime at 25% efficiency, we see like 1.6 times B rejection and twice X the light rejection. Okay, so next coming to some ablation studies. So ablation is essentially you take your network, you remove the component, and you see what happens to the performance. So this was very interesting for us because we wanted to see how the auxiliary task performs. How is it helping us in this case? So that's why you have more curves on the plot this time. So you have the DL1R, you have the GN1. But additionally, you have you have a version of GN1 where it just has vertexing auxiliary task, and then it has a version where you only have the track classification auxiliary task, and also one more version where you don't have any auxiliary task. So the message is kind of clear, like as you keep removing auxiliary tasks, the performance goes down. If there is no auxiliary tasks, it's kind of the worst performance out of those. And if you combine both the auxiliary tasks with your primary tasks, you get the best performance, which kind of confirms that like the auxiliary tasks are kind of complementary to each other. Additionally, we can also separately look at the performance of the auxiliary tasks to some extent. So we looked at the vertexing performance, and we saw that GN1 can find like 80% of the displaced vertices that we see from B-hadron decays. And to look at what's happening with track classification, it's not very trivial. So what we ended up doing is to create like a baseline multi-layer perceptron model. So it takes the same inputs as GN1, but it processes one track at a time. So it takes it as a track as an input and tells us its origin. And we saw that GN1 outperforms the baseline MLP on both TT bar and Z prime. So on the plot, you can see the ROC curves for GN1 on TT bar and Z prime for different origin. And using those, like from this ROC curve, you can also compute the area under the curve. And the table shows the area under the curve, and we see that the GN1 shows like a better track origin classification compared to the baseline MLP. And the kind of the explanation here is that GN1 allows this mixing of information among tracks, which is not there in the baseline MLP. So that certainly helps. And additionally, like if you look at things from the track classification perspective, the flavor prediction and vertexing can also be considered as auxiliary tasks. So they also somehow help in track classification. So that's kind of all with the performance. But additionally, I want to mention that the GN1 is very flexible. So what I mean is that since it's like a very lightweighted in terms of number of components, so it's very easy to optimize it for new region of the phase space, or when you do something with the detector or change like how you reconstruct charge particle, you can kind of get away with by just retraining the model. And also if you find, let's say, some new physics signature that you think will be helpful in identifying the flavors, So adding this to this architecture is also kind of straightforward because this can just be in principle another auxiliary task. And also if you think like there's another set of variables which will be helpful in cyber tagging, then it can also easily accommodate those variables. So yeah, that's kind of bring us to the summary. So we talked about this new graph neural network based flavor tagging tool developed in Atlas. And we indeed got an all-in-one tagger, which is what we wanted to discuss in the beginning. It shows improved performance with respect to DL1R on simulation. And the main ingredient behind this improvement turned out to be the auxiliary objectives that we defined, namely the vertexing task and the track origin classification. And it's quite flexible and it can easily be adapted to other specific use cases. And we have a pub note, which is supposed to be released like very soon. Maybe by the end of this week, it should be public. And the current status of GN1 is that it's fully implemented in Athena, just like the Atlas software, and the calibration studies on data will follow very soon. Okay, so that's all from my side. Thank you.
Many thanks. Shall we just first ask if there are questions on Zoom? Don't see any. There is no. We haven't. Did you have the Q&A button up to see if there's any? I do now, but yeah. Otherwise, in the room. Yeah, let's start. I'm gonna start at the front with Lava.
Okay, thanks for. Okay, this is Alva. Thanks for your talk. Concerning your plot on page 8. Yeah, okay, well, it looks like okay, you have some gain with the GN1. But what about the separation, I mean, between the different flavors? It's not clear to me that you gain much or...
Right, so this plot doesn't really say much about like how much gain you have. As you saw, but yeah, but if we look at like just B tagging performance, so you can see the P distribution is slightly shifted towards right, and charm and light are like shifted towards left. So that's it kind of just gives you a very qualitative idea, not like a quantitative picture. So that's why we look at these like rock curves, which kind of gives you exact numbers like this. If this is your B tagging efficiency, then this much is your rejection for the same efficiency.
Okay, thanks. Then I have a second question. On your list of variables, when you run this algorithm, you have a ranking of the variables at the end?
No, we haven't looked at that yet. No. Some rough intuition about some of the variables, but no, we don't have a ranking at the moment. Something you'll have to look at. Yes.
Thanks. Thanks, Joe. You had to.
Yeah. Hey, I'm Joe. So I had a question about your sort of last two slides where you talked about the flexibility of the algorithm. And in your summary, you say it can easily be adapted to other specific use cases. Is there any work, and maybe this is a general question too, towards machine learning, heavy flavor jet tagging algorithms? Is there any work to make these algorithms available to the community so that they can be implemented or used in other experiments?
Right. So currently we have some effort in Atlas to look at like, I don't know, the will be tagging or just because we looked at these high PT plots as well, right? So which is also like one of the specific use cases, I guess, because otherwise you have to tune everything for low PT and high PT, but in this case, like we can just directly get something that works also on high PT. But additionally, yeah, of course, like boosted tagging is like something that we are interested in. But these are at very early stage because this one its pub note will be out soon. So this one itself is at an early stage, but so hopefully in the future we'll have more spin-offs.
But in principle, the the code structure should be such that you can provide this. You give a list of features, which you even say they are changeable.
Right.
Then there's not much. Let's say there's not much needs that it's a very detector experiment dependent. So one could really think of providing this. I think that's what you are aiming at, Joe.
Yeah, so on one of your, on the input slide on page 6, most of these variables are very generic to any experiment, other than the sort of hit information, which may depend on your particular detector configuration. So in principle, yes, Andy, that is kind of what I was thinking, that you could somehow make a commonly available machine learning algorithm where you just have to input these generic features and then maybe some specifics about your detector and see if you could then tune it or train it in a way to achieve similar performance.
You know what? You should suggest this to the HSF construction working group leader, being me, to make a topical meeting about this, because I think that's a very good suggestion that we tackle this in one of the in the context of the HSF, and they can make these taggers reusable. It will also, I think, teach us something how much you can take a pre-trained model already from some experiment and then, let's say, do some transfer learning on another detector. I think that will actually be a nice study. Good.
Right. Yeah. So, and from the construction point of view, it's pretty doable. Yeah, we haven't really discussed much about it, but yeah, that's a good idea.
Yeah, I think we'll follow this up. This sounds pretty much as a HSF topic, I would suggest. Good. Then we go to the